Hi guys, welcome to Learning Electronics Repair. We've seen this before several times. So this is the power supply off the amplifier, Class D amplifier, that had short circuit MOSFETs in. I replaced them, checked everything I could using the multimeter, looking for shorts, whatever, on the various components. All looked okay. I ordered some from AliExpress, fitted them, and after a couple of 3 seconds they blew up again. Okay, and that was with no load on the power supply. It wasn't connected to the amplifier board. I had some working ones of these here previously. I don't have now, and I do know that you can disconnect the load from this. It does work, by the way. We should have coming out here roughly plus and minus 70, and then we have a plus and minus 15 on these white connectors. So this blew the MOSFETs even with a current limiter on. And I explained on the previous video why that was and how we could prevent that from happening. I then made a second video, and in the second video I reverse engineered most of this, figured out how it worked, figured out how to power this circuitry up without the mains applied, and I can see I've got a good drive waveform going to the MOSFET. So the drive waveform looks good, and at the time the best reason I could come up with why the MOSFETs blew is they were probably fake ones from AliExpress. So I ordered some genuine ones. These were from LCSC. They provide good quality components, so I'm happy to do that, and they're here. So I think I bought 10 of them, MOSFETs, for this. And I want to fit the MOSFETs and see if this now works, but what I don't want it to do is blow up again. So I need to figure out how to limit the current. Now, I'll just draw on paper what we basically have here and why this is not quite as straightforward as you might think. So the basis of this power supply, we have live and neutral coming in. We have some filter capacitors, the usual sort of thing, inductor, filter capacitor. I think there's a thermistor like NTC. Yeah, there's an NTC in here. It actually has a relay wire across it which switches it effectively to short when the thing's powered up, but that's neither here nor there really. And then we have the bridge rectifier, AC, plus minus, okay, and coming out of here. We have about 320 volts DC. Now, this is wired up similar to an ATX type power supply, half bridge LLC circuit. So 2 large electrolytic capacitors and 2 MOSFETs. These are the ones that blew up. Okay. These are driven by the pulse width modulator via a little transformer, actually. Like a little drive transformer like this, I think it is. It has some resistors as well. It has some transistors in here. Those ones there. This is the little transformer I've just shown you, and that's the controller, the pulse width modulator. So I won't draw all those transistors, but basically this is pulse width modulator IC, okay? And this transformer, basically the PWM can send via the transistors current first in one direction, then in the other, and these other secondaries are wired up in such a way that if we take this as the positive end of this coil, that's the positive end of that one, but this is the positive end of this one. It's the other way round it reverse phase. So as the current passes one way, it puts a positive onto this MOSFET and switches it on, and as it passes the other way, it puts a negative on there and a positive onto this one and switches this on. That's how it switches backwards and forwards. Okay, so that's what we have. Then we have our transformer. Now normally on a circuit like this, you would have a large high voltage capacitor here, and this would drive one end of the transformer winding. Okay, ours isn't like that. So on ours, we have a high voltage capacitor here, and this is the primary of the transformer winding. Okay, connecting to there. So that's how the high voltage circuitry works, the switching transistors. Now, initially I put, and we'll draw the fuse, there is a fuse in here. I put my light bulb on the end here, so effectively this was my light bulb connected to the mains wiring, okay, like that, into my power socket. Well, I'll draw a different symbol for a light bulb because people were moaning about the one I use. Okay, so I put my light bulb there. The thing powered up. It has a soft start circuit. It takes a couple of seconds. This started running and those went bang. They went short. They didn't actually go bang because the light bulb just came on bright. Nothing went bang, but it blew both MOSFETs. Now, the reason this 60-watt light bulb didn't protect the MOSFETs is because at this point, because of the soft start, these capacitors had already charged up to 320 volts. Okay, the soft start takes a few seconds before this gets power, VCC. Okay, and when this got VCC, this started running, it started switching these. That's when it failed. Now at this point, you've got 320 volts charged up in these capacitors. So although my current limiter is there, these can provide a huge amount of current. Through there to there. And it went bang. The discharging capacitors were enough to blow the MOSFETs. Now, I need to connect my light bulb in such a way that that doesn't happen. Now, the only way this blew was for two reasons, really. One is that both of these switched on at the same time, or MOSFETs were just not high enough rated to handle the current and voltage. When the circuit's operating, basically, in the first phase, if you like, when this one is switched on and this one is switched off, the current is flowing, as I've shown through here, through this capacitor, because this is AC, it's a high voltage pulse, through the transformer winding to there. So that's where the current is flowing, because this one is switched off when that one is switched on. Okay, so that's what should happen. And then when this one switches off and the other one switches on, okay, when that happens, the current should now flow from here through this MOSFET to there, that way. Okay, so we have two current paths, and this one, the current is flowing this way through the transformer winding, and then the other way it's flowing that way through the transformer winding. Okay, so the question is, where do I put the light bulb if I want to stop these blowing up? I could put the light bulb here. I could disconnect this drain and connect the light bulb effectively here. Okay, so the current flows through my light bulb. Okay, I could do that. That will limit the current flowing through this MOSFET during this part of the cycle, but it won't limit the current flowing through that MOSFET during the other part of the cycle. The other problem with that, it's tricky to do, so I'd have to either cut the track or in some other way, lifting the leg, connect the light bulb. Okay, There's another way I can try this, and that is to connect my light bulb in here. There, okay. So what happens now when this MOSFET switches on? The current flows via the capacitor light bulb coil, okay? And then when that's off and this one's on, it flows this way. So the current now, no matter which one is switched on, will flow through the light bulb. So that should prevent the MOSFETs from blowing up, but only if both don't switch on at the same time. Now, I know from the previous video, which I will link, that this is working properly. So basically, the waveform is correct. There's a dead time in between. So if you like, the drive switches this one on. Okay. At that time, it switches that one off. But there's like a gap, so it's hard to draw it. Before this one switches on, the other one switches off. So there's never a point when they're both on, yeah? Sort of like that. That's the best way I can describe it. I showed it on the video. You can see the waveform on the scope much better than my drawing. But I know that is correct. So I know for a fact that both transistors, MOSFETs, are not being switched on at the same time. I can see that. Why else would the MOSFETs blow if it wasn't because they are fake? Well, I know there's no short circuit on the output. I've tested that. There are no shorts over here. So there's no short on the output of here. I've proven that all this works okay, that the MOSFETs are getting switched at the correct times. But what I can't prove, and this is difficult to do, is whether this transformer is faulty and it has a shorted turn somewhere in the winding. Okay? If that was the case, what you end up with is your primary, your secondary. I think this transformer actually has two secondaries, one auxiliary winding to power that, and another one to power the output, and it probably has a third one as well to power the low voltage output. So we have the just try and draw it a bit. We have the plus and minus 15 coming from here via rectifier diodes and capacitors, of course. We have the plus 70 and minus 70 with a center tap, and again obviously diodes and capacitors to generate those. We have this one, which is the auxiliary winding, which powers this up. We have those three secondaries. This is our primary. Okay. Now, if we get a shorted turn, and it's normally in the primary, but it doesn't have to be, it can be anywhere. A shorted turn, you might think, well, if there's like 500 turns on here, and I've now got 499 turns, what's the problem? Well, the problem is that the shorted turn is another secondary, effectively. Once the turn is shorted, it becomes a secondary. So we have another secondary with just one turn in it. Okay? And that will generate a very low voltage at a very high current because it's only one turn, yeah? You know how this works. If the primary has, for example, 100 turns, it has 220 volts, let's say 1 amp, then an output, if it was 20 volts, like 22, let's say this one was 22 volts, this would be able to give us 22 volts at 10 amps, a tenth of the voltage, 10 amps of current. Obviously, the maximum of all the windings added up together will have a limit, but that's basically how it works. And this winding is like probably like 0 point whatever volts at a very high current, yeah? So having a shorted turn on the transformer is the same, effectively, as having a short circuit on one of these outputs. Yeah, it puts a huge load on the transformer. And depending on the circuit, the PWM might shut down, some protection might kick in over current or whatever, or it might just blow up. So from all that, a lot of talking, but I hope it was worth it. The problem with this is either going to be, I think, faulty output devices that were just fake, or a shorted turn in here. Yeah, everything else has been tested. And the best way to protect against that is to put a light bulb in here. So if I do this, and the light bulb doesn't come on, or comes on dimly, or just flashes once and goes out, I can say basically there's no current flowing into here. And with no outputs connected, well, that's what you would expect, very low current. And if these are switching, then I know these are good. If these blow up anyway with that there, and the light bulb maybe not even light up, then I know that there really is something wrong with this drive or these MOSFETs, even though it looks okay when I trace it through with my scope. So I'm going to put it there. You guys let me know what you would do, but that's where I'm going to put the light bulb. And this is easy because I can unsolder the capacitor, lift one leg out of the board, solder a wire to the board, a wire to the end of the capacitor, and that's where my light bulb connects. While I'm just unsoldering my capacitor, I've thought of a third reason why this could blow up. And the third reason is, although I can see the waveform here, and it looks okay, it's running at about 45 kilohertz. And it may be that it's due to some fault on the board, and it's probably a high value resistor, and the timing for this, it's running at a frequency that is too low, so that this is saturating. The fact it's connected via a capacitor, I'm not sure if that would cause it to blow up or not due to the design, but if that transformer coil saturates, that is not a good thing at all. So it may be an outside chance that the PWM is running at the wrong frequency. Let's have a look at these MOSFETs. So these ones, and I have 10 of them, are the ones I got from LCSC, okay? So we can see port number IFPFZHDO. Okay. We see the markings on them. So I have 10 of those, and these are the ones I got from AliExpress. So completely different marking, but these have the international rectifier stamp on, where the other ones don't have. Same part number, IFP460. But I'm sure if I put these onto my component analyzer, it will just say they're N-channel MOSFETs. Let's have a look. So these are some of the new ones. I know the other ones before I fitted them told me they were N-channel MOSFETs, all right. So let's try. And I also checked the pin out was correct, but let's make sure they match. So this is one of the new ones. N-channel MOSFET. So green is the drain in the center. Voltage threshold 3.34. Okay. Another one. Green drain, yeah. 3.38, so that's slightly different. This one. 3.38, same as the previous one. Okay. Well, they're all basically the same. I imagine they would be. What's this saying? .36. So they're all very similar. I have two that are reading 3.38, so I'll keep that on one side. Those. How about these ones? So again, we've got green in the center, which should say it's the drain. Okay. And channel MOSFET. drain in the centre. Oh, 1.86. Try another one. It's 1.82. These are much different from the other ones. Well, there, guys, there's a big difference. The gate threshold is much lower on these. Yeah. Huh. These have a much more sensitive gate than those other ones. They must be different MOSFETs. I mean, we're going from like 1.8 volts to like 3 points. What was it exactly? 3.3? .38. Wow. 1.5 volts difference there. Well, these are clearly not the same as those, yeah? And because we know that the gate of these is driven via a transformer, and these are very sensitive, that makes me wonder if that's why, most likely, they switched on and stayed on, or didn't switch off properly or fast enough. So, I'm even more confident now that these are actually fake MOSFETs. And I think I have a good reason I can see why this didn't work. So rather than tempting a bit of fate, because any modification like putting the light bulb where I said is a modification, and given the fact I can see a big difference between these MOSFETs, I'm actually going to fit two of these, just put my light bulb limiter in series like it was before with the mains. I'll put that capacitor back in where it came from. And let's see if it works. I know the light bulb limiter might not save the MOSFETs, but it will save the thing from going bang. So let's see. And if it doesn't work out, I have 8 more of these anyway. Okay, so I fitted the MOSFETs, they're back in. You see soldered there, okay, nice and clean. I put the capacitor back in. The change of mind on the way I was going to go with this, I do this a lot, you know that, guys. When I saw something obvious like the gate voltage on those MOSFETs, then I'm thinking obvious reason why it failed, so therefore why mess about, yeah. It may fail again, but then we can go down the other route. I'll just put the camera where you can see the light bulb, which is just tucked back there, you can see it. I am set to limit, I have the power on. This is connected to the output. For whatever reason, I see 0.9 of a volt on there. Yeah, a little bit of charge in the capacitors by the looks of it. Okay, so let's switch this on and let's see what it does now. Light bulb, here we go. It's working. Do you see that 50 volts, 52 volts? So it no longer goes bang, yeah? Did you hear the click, maybe? That was the relay clicking in across the thermistor. The capacitors obviously will hold quite a charge. It's on the negative output. Same. Okay, so that power supply now works. We can see what was wrong with those MOSFETs, but without having a good one to compare with, I don't really see how you would have found they were faulty. Really, I did this just by elimination of, there was nothing else wrong, basically, apart from, as I said, I couldn't test for shorted turns in the transformer, maybe. Okay, so the amplifier PSU works. What we need to do next with this is to fit this back on and test the amplifier. I think I will probably test the amplifier because it's had some short circuit output devices. See if I can power it up with my bench supply first, because I've got a very strong feeling that the fault on the amplifier is what blew the power supply on this initially, and I really don't want to go back down that route again. Okay, anyway, hope you enjoyed that. Not too long. interesting chat, I think, though, about how to go about this sort of work, and we had a result. I look forward to seeing you all again soon then on Learning Electronics Repair. Ciao for now, guys.